Welcome to The Explainer. Our whole deal here is to take complex source material and break it down into a clear, focused explainer. And today's topic, well, it's a big one.
Okay, so let's just jump right in. Think about the number pi. 3.14159. It's been a cornerstone of math and science for, well, centuries. It's a number we all just take for granted. But what if it's wrong? What if that constant isn't so constant? That's exactly what we're going to explore today. We're looking at a theory from our source material that basically throws down the gauntlet and challenges one of the most fundamental constants we have.
So, get this. The source material we're looking at makes this absolutely wild claim. It says that in the real world, the world of physics where things are actually moving, the true value of pi isn't that endless decimal we memorized. Nope. It's exactly 4. So how on earth do we get to a claim like that? Well, here's how we're going to break it down. We'll start with the radical claim itself and how it questions Newton. Then we'll get into the new model of motion and time it suggests. After that, we'll look at what it calls proof, the so-called explorer anomaly. And finally, we'll touch on what it would mean if any of this were true.
All right, so first things first. Before we get into the how, let's be super clear on the what. The theory we're exploring isn't saying that pi is wrong for everything. It says that our standard geometric pi, the one from school, is perfectly fine for static shapes on paper, a perfect, timeless circle. But the second you introduce motion, like a planet whipping around the sun, or even just the physical act of drawing a circle, that's when, according to this source, 3.14 just doesn't cut it anymore.
Okay, so to even begin to make a case this big, you have to go after a giant. And that's exactly what the source material does. It tries to pull apart the very bedrock of calculus, a fundamental proof laid out by Isaac Newton himself in his legendary masterpiece, the Principia.
And let's be clear, this isn't some minor quibble or a little tweak. The argument starts by saying, hey, you know that thing Newton said that we've all accepted as gospel for over 300 years? It's wrong. It's a direct assault on a foundational idea.
So what's the beef with Newton? It really boils down to how you measure a curve. Newton's whole idea was that if you zoom in far enough on any curve, an infinitely small piece of it, that the curved line, the straight tangent touching it, and the chord cutting across it all basically become the same length. They converge. But the source material comes back and says, nope, not possible. Physically impossible.
Their whole argument hinges on this diagram. The idea is, as you slide point B closer and closer to point A along the curve, that angle at B gets closer and closer to a perfect 90-degree right angle. And what do we know about right-angled triangles? The hypotenuse, in this case the tangent line, is always longer than the other sides. It has to be. So the source argues the tangent and the chord can never become equal, not even at the infinite limit.
So, if we follow this line of thinking, if the very foundation of how we measure curves is flawed, then what's the alternative? What do we use instead?
And that brings us to the core of the alternative idea, something the source calls a kinematic model. The argument is simple, really. You can't just separate geometry from the time and motion it takes to create a shape in the real world. A circle drawn with a pencil isn't just an abstract shape, it's a physical event that unfolds over time.
And this distinction, according to the source, is everything. You have the geometric circle, a pure, timeless idea, and then you have the kinematic circle, a physical path traced by something moving through time. The argument is, you just can't measure an abstract concept and a physical event with the same mathematical ruler.
So, how do you measure this kinematic circle? Well, instead of using calculus and chords, this model uses what you could call a city block method. Imagine you're trying to get from one point to another on a curve. Instead of a direct line, you can only move horizontally and vertically, like walking on a grid. You take a little step right, a little step up, another right, another up. The key claim here is that no matter how tiny you make those steps, infinitely small even, their total length, the distance you walk around the block, never changes. It always adds up to the same final number.
And the source provides a great illustration of this. Think about a point on the edge of a rolling wheel. The path it traces is called a cycloid. And it turns out the length of that cycloid path is exactly 8 times the radius of the wheel. The source calls this the kinematic circumference. So if the circumference is 8r, and we all know the standard formula is circumference equals pi times the diameter, which is 2r,
Well, you do the math. What's 8r divided by 2r? It's 4. That's how they get to a pi value of exactly 4.
So here's the side-by-side according to the source material. You've got the geometric model for static shapes, giving you a pi of about 3.14. And then you have this new kinematic model for things in motion, which gives you a pi of 4.
Okay, but this is all just theory and math, right? Well, the source claims there's real-world smoking gun evidence for this idea, and it points to a very famous series of screw-ups from the dawn of the space age.
Think back to the late 1950s. The space race is on. But there was a huge problem. The source highlights that rockets from both the Americans and the Soviets were consistently, and I mean dramatically, missing their targets. The math just seemed to be flat out wrong.
And the Explorer 1 incident, America's first satellite, is the poster child for this. This wasn't a tiny miscalculation. The orbit was so much higher than predicted that flight controllers literally thought they had lost the satellite. The signal was 12 minutes late. They thought it was gone.
And here's the bombshell calculation from the source material. It claims the total error in those 1958 orbital equations was a whopping 19%. Now, guess what the percentage difference is between an equation using the traditional pi and an equation using a pi of 4? You guessed it, 19%. An exact match.
So what happened? The source argues that this huge discrepancy was never really explained from a physics perspective. Instead, it suggests that engineers just fixed it. They tweaked the equations, added what amounts to a fudge factor to make the numbers work, and moved on, essentially papering over a fundamental flaw in the physics without ever addressing it.
So let's just imagine for a second that this theory is correct. The implications, well, they aren't just a quirky historical footnote. They would send shockwaves through pretty much every field of modern science.
I mean, the claims here are enormous. We're talking about rewriting the very foundations of calculus, challenging key assumptions in Einstein's general relativity, potentially getting rid of the need for complex mathematical fixes in quantum electrodynamics. It would rewrite all the equations we use for orbital mechanics. Heck, it even suggests that the way we measure a 400-meter Olympic running track is fundamentally wrong.
So, you see, in the end, the argument presented in the source isn't really about memorizing a new number for pi. It's about something much bigger. It's about shifting our entire perspective on how we even think about measuring curves, motion, and reality itself.
Look, the source material lays out a provocative and honestly pretty detailed case that goes up against centuries of accepted science. So it leaves us all with a pretty big question. Is this a suppressed truth that's been ignored for decades? Is it a profound misunderstanding of how calculus actually works? Or is it all just a fascinating mathematical fantasy? That's the question we're left with.